here, what we're going to do is learn how to optimize functions. Now, we know a little bit about optimizing functions with the extreme value theorem, and what we're going to do here is apply the extreme value theorem and some of our mean value theorem observations to functions that describe something useful. So first, we're again going to observe these two types of graphs. So here we have the top of a mound giving a maximum. Here we have the bottom of a mound giving a minimum. A lot of Chapter 4 reduces to a very precise understanding of these two types of curves, or if it had a point on top instead of a mound, using calculus. So notice when we have a maximum, before it gets to that maximum, the function is increasing, and after it's at that maximum, it's decreasing. And similarly for a minimum, before it hits the minimum, it's decreasing, and after the minimum, it's increasing. So let's make a couple observations about these. First, we'll notice, as we've noticed before, a maximum or a minimum will occur when f prime is 0 or when f prime is undefined. Next, if a maximum occurs at x, then it's increasing on the left and decreasing on the right, but with derivatives, f prime is positive on the left of x and f prime is negative on the right of x. And similarly, for a minimum, f prime is negative to the left and f prime is positive to the right of x. Now, this last observation we haven't noticed before, we haven't observed directly before, but in these problems, what we're going to do is find where the derivative is 0, where it's undefined, and then we're going to have to interpret them. And to do that, we're going to have to somehow use calculus to differentiate between these two. You could do that with these 2 points, but it is frequently more useful to use this last point. So finally, notice, if a maximum occurs at x, then f double prime is negative at x. Well, remember, the second derivative tells us about concavity. So right here, if a maximum occurs at x, notice it is concave down at x. So we could use these second and third bullet point first derivative observations to reach our conclusions. But down here with this last bullet point, we could also use a second derivative observation to reach our conclusions. And in many cases, this is easier because, like up here in these second two, you have 2 derivatives to check. You need the left of x and the right of x, or 2 signs to check. But down here, all you need to observe is the second derivative at x. If it's negative, it's concave down, so you have a maximum. And similarly, if a minimum occurs at x, then it's concave up at x, which gives you, or which you can see by taking the second derivative and observing that the second derivative would be positive at x at the bottom of that mound. I forgot what I was going to say halfway through my last sentence. Well, let's do some examples. It'll come back to me. Now, optimization examples could be phrased something like this. A farmer has 2,400 feet of fencing and wants to enclose a rectangular field that borders a straight river. What dimensions maximize the area? So right here, this last part, maximize the area, that tells you the function you want to do calculus on. We're trying to maximize area, so we need to do calculus on an area function. Frequently in these, it's useful to draw a picture. So let's draw this field. Wants to enclose a rectangular field that borders a straight river. Borders a straight river in math implies that you do not need fencing on the river. So maybe I'll just put as a parenthetical, no fencing on river. Maybe cows are afraid of water or something. I don't know. I've never farmed cows. I don't even know if that's the proper phrasing. Although there are a lot of dairy farmers up here in Wayne County. A farmer, 2,400 feet of fencing, wants to enclose a rectangular field that borders a straight river. What dimensions maximize the area? Well, let's say the river is down there. So right here we need fencing there, we need fencing there, and we need fencing there. It's rectangular, so the This side is different from this side, so let's call that x and the other side y. What dimensions maximize the area? Well, we need an area function. Area equals x, y. Well, that's great. We have a function of two variables. We do not know how to deal with functions of two variables in Calc 1. That is a Calc 3 topic, maximizing functions of multiple variables. But here, we're given other information in the question, and that other information will allow us to remove one of those variables. What other information do we have? Well, 2,400 feet of fencing. So this plus this plus this makes 2,400 feet. So 2x plus y equals 2,400. In many optimization problems, one of the goals is to find two equations. One that we're doing calculus on, and another constraint that will allow us to eliminate one of the variables in the function we're doing calculus on. So we have the function we're doing calculus on, which is area function, we're maximizing the area, and we have this constraint on the variables. Well, let's now get area in one variable. Area equals xy. Let's write that a little differently, while in a different position. So area equals xy, but y down here equals 2,400 minus 2x. Solve this for y, you get y equals 2,400 minus 2x. Well, that's nice. That's a function of one variable. Let's distribute that x. Well, that's great. Area is now 2,400x minus 2x squared, function of one variable. Well, now we know how to maximize functions of one variable. We're going to want to show that it looks like this, because that'll give us a maximum. And we then want to make sure we answer the question, what dimensions maximize the area? We need an x and a y. So let's do the first derivative. 2,400 minus 4x. We want where it's 0 and where it's undefined. It's never undefined. Where is this 0? This equals 0 when x equals 600. Because 2,400 minus 2,400 is 0. Well, we have this point x equals 600. Well, if x equals 600, what's y? 1,200. Y is 1,200 from this constraint equation. Substitute x equals 600, solve for y, you get 1,200 plus y is 2,400, 1,200 equals y. So you might be tempted to stop right now. You found dimensions that'll maximize the area. But we haven't shown that this actually gives us a maximum. This could, for all we know, give a minimum. So we have to show that this gives a maximum. So I'll say, well, there are two ways we could do it. We could show it gives a maximum by showing it's increasing and then decreasing around 600, or we could show it's concave down. Here, let's show it's concave down. A prime prime equals what? Negative 4. Negative 4, which is a negative number. The second derivative is negative. So x equals 600, y equals 1,200, gives a maximum. Now, one convenience of calculus is when we were doing graphs, there were positive sounding words going with positive derivative results. So when the first derivative was positive, it was increasing and concave up. Those are all positive. When the first derivative was negative, the function was decreasing, and concave down. Those are all negative sounding words. And right here, we have something that seems like it might go contrary to that. We have a negative going with a maximum. And I find that quite difficult to remember. But what I don't find quite difficult to remember is graphs that look like this or that. So whenever I do one of these and I take the second derivative, I always like to think of what that actually looks like. So here, the second derivative is negative, which tells us the function is concave down, which tells us the point we found is going to be at the top of a curve like that. So this gives a maximum. This question did not ask for the maximum area. It just said what dimensions maximize the area. That's not the same as what is the maximum area. So you don't have to find the area. The area is what, 72,000? But you do need the dimensions. Let's do another of these. Slightly different question. The sum, or was that sum or difference? The sum of two numbers is 16. Minimize the sum of their squares. The starts with T. The sum of two numbers is 16. Minimize. Wow, I'm bad at spelling today. Minimize. The sum of their squares. So the sum of two numbers is 16. We want to minimize the sum of their squares. So again, we have an optimization question. The first thing I like to do with that, well, the first thing I like to do is draw a drawing if a drawing is relevant. Here, a drawing is not relevant. And when a drawing is not relevant, the first thing I like to do is identify the function we're doing calculus on. Minimize the sum of their squares. Well, x squared plus y squared is the sum of their squares. So we're doing calculus on this function. Now it's a function of two variables. So let's eliminate one by using the other observation that x plus y must equal 16. Well, if that's the case, let's call this capital S, x squared plus y squared. I always like doing calculus with x's, so let's eliminate y. Y equals 16 minus x. Y equals 16 minus x. Distribute that through, and what do you get? You get x squared plus 2, 5, 6, negative 32x positive x squared, which equals 2x squared negative 32x positive 256. Well, okay, now we just need to show this or this. In this case, we're going to be showing minimums. We're going to be showing the second of those. So let's do that. S prime equals 4x minus 32. This equals 0 when x equals 8. Well, we need to show that this gives a minimum. So let's do that with the second derivative. Second derivative equals 4, which is positive. Positive means what? Concave up. Concave up would tell us that that point x equals 8 we found would give us a negative, or give us a minimum. So x equals 8 gives a minimum. Now let's go back and see what question we were actually asked. Minimize the sum of their squares. Well, we're going to need a y value too. If x equals 8, then y equals 8 also, because 8 plus 8 is 16. So that gives a minimum. We want to minimize the sum of their squares. So x equals a, y equals a gives a minimum. And I'll just say I used s up there, so there's s. S equals 8 squared plus 8 squared, 64 plus 64, which is 128. I wrote 124, I think, because I was saying 64. So S equals 128, and that's a minimum as we observed over here. So you could be asked an example like that, where it's just, here are some numbers, here's some information on some numbers, turn them into equations, and do calculus. But notice the similarities between that and the first one. You had two functions, one you were doing calculus on, one you weren't doing calculus on. The original, or one of the functions was two variables, so you eliminated a variable up there, and then you just proceeded with the first and second derivatives. And of course, you could have done this minimum analysis using the first derivative by showing it's decreasing and then increasing around x equals 8. At 7 it's negative, at 9 it's positive, so at 8 you have a minimum. Let's do another example. A pizzeria. How do you spell pizzeria? E-R-I-A. Sells pizza. That's nice. For $13 each. That's a lot of money for a pizza, I think. Those of you, well, some of you may think $13 is very cheap for pizza. When I was growing up in the 90s, there were pizzas, good pizzas up here in Northeast Pennsylvania, for $4 each, or $5 each. 13, it's awfully high. Where were we? Pizzeria sells pizza, $13 each. The cost to produce X pizzas is cost function. Let's write it down here. The cost to produce is a cost function equals 13 negative 11x positive 3x squared. 3 parts. Find the revenue from, 2 parts. From selling X pizzas. Part B, how many pizzas must be sold to maximize profit? So 2 parts. Find the revenue from selling X pizzas. Part 2, maximize profit. So let's first do part A. Revenue equals what? Well, selling X pizzas, revenue is how much money the pizzeria brings in from pizzas. Pizzas sell for $13 each. The revenue from selling X pizzas is 13x. $13 per pizza times X pizzas. Part B. How many pizzas must be sold to maximize profit? Well, let's get a profit function. This should probably say either they only sell pizza or maximize profit on pizza. But whatever. Profit is revenue minus cost. Profit is revenue minus cost. So profit, so let's say P of X equals revenue. Oh, it's over here. 13x minus cost minus 13, careful with the negative signs here, negative 11x, positive 3x squared. Let's simplify that. What do we get? Negative 3x squared, positive 24x, because it's 13 plus 11x, minus 13. We're doing calculus on our profit function. Our profit function is already a function of one variable. Is that the answer? Yeah, okay, 4 is the answer. Our profit function is already a function of one variable, so we don't have to do any substitution. We can just jump straight into the calculus. P prime is negative 6x plus 24. This equals 0 when x equals 4. And this gives a, well, we're going to show it gives a maximum since, well, let's do a second derivative. Second derivative is negative 6. The second derivative is negative. When the second derivative is negative, the function is concave down. When it's concave down, the critical point will be a maximum. So here, we needed to first find the revenue function. It's just the number of things you sold times how much you sell them for. Then the profit function, revenue minus cost, how much you take in minus how much you spend out. And then do calculus on that profit function. Let's do two more. Let's do two more optimization questions. Let's not do that one. Let's do this one. Of all, so show, well, prove this statement. Of all rectangles with a given perimeter, the one with the largest area is a square. So show of all rectangles with a given perimeter, the one with the largest area is a square. Well, let's start writing equations. Maybe it'll become more clear what we're doing with a couple equations. Of all rectangles with a given perimeter, so let's take a rectangle and fix its perimeter. So here's a rectangle, x and y. P is a constant. Of all rectangles with perimeter P. Okay, that's great. There's an equation. The one with the largest area is a square. So here we're doing calculus on the area function because we want to show largest area, and then we're going to conclude it's a square. How would we be able to conclude it's a square? Well, you'll see our final conclusion would be that x equals y. So right here we have an area function we're doing calculus on, but it is of two variables. Let's eliminate one. Let's eliminate y again. Solve this for, what are we solving for? Y. Solve it for y. You get p minus 2x divided by 2. Wait, what do you get? P, oh, no. P minus 2x divided by 2. Solve this for y. Subtract 2x. This is p minus 2x. Divide by 2. And now let's just simplify this. So it equals a half x times p minus 2x. And that equals what? p over 2x minus half and 2 cancel. P, oh no, not a p. So distribute a half x through. P is a constant, remember. So p times a half x is just p halves x, and then a half x times 2x is x squared, and then there's a negative on that last term. So p is a constant. Well, we have our function of one variable now. So let's take the first derivative. P over 2 minus 2x, and let's set this equal to 0. How do we solve this? Well, let's isolate x. So add 2x to everything. Add 2x, divide by 2, you get x equals p over 4. Well, there's one observation. X equals p over 4. Well, let's show next that this gives a maximum. So I'll write down here, maybe I'll write it like this. A prime prime is negative 2, because p over 2 is a constant. That's a negative number. When it's negative, the function is what? Concave down. The function is concave down, so that gives a maximum. So x equals p over 4 gives a maximum. Well, that's great. We showed that x equals p over 4 gives a maximum. We didn't show that x equals y. We've shown x equals p over 4 will give us the largest area. Why does x equal y? Well, let's use our perimeter constant. So if x equals p over 4, then what? 2 times p over 4 plus 2y equals p into our perimeter equation. 2 and 4 make a half. So a half p plus 2y equals p. If you have a half of a p over here and a full p over there, subtract the half, you get 2y equals a half of p. Solve for y, you get y equals p over 4. So you get y equals p over 4, you have x equals p over 4, so it's a square. When the area is maximized, it's a square. So here, p is a constant was the key observation. There's a parallel observation, or parallel example of all rectangles in a given area. The one with the smallest perimeter is a square. So that kind of flips it around and says area is your constant and p is the function doing calculus on. You should try that. It's quite similar to this. Let's look at one more example. So next, a right circular cylinder is inscribed in a cone with height h and base radius r. H and r are constant. Find the largest possible volume of a cylinder. Well, here we have a cone with height h and base radius r. So a right circular cylinder is inscribed in here. What would that look like? Well, that would look something like this. Let's draw it like that. And then we have the cylinder. The bottom would match identically with this bottom. We'll find that thing about what the bottom actually looks like. It doesn't matter. The real information can be contained up here, or is contained up here. So a right circular cylinder is inscribed in this. Now we need to find the largest volume of the cylinder. So we need a volume of a cylinder to do calculus on. Well, with the current variables, well, there aren't variables, but with the current labeling, we can't really find the volume of a cylinder. But let's label a couple quantities that are variable based on where the cylinder. This cylinder could be like this. It could be way down here for all we know. It could be way up here and pretty narrow for all we know. So this height is a variable quantity. Or this distance, I should say, is a variable quantity. I'm going to call it y. The other variable quantity is right here. the radius of the cylinder. So the height and the radius of the cylinder are variable, but we'll see that labeling that distance, using that to identify the height will be useful, since we've already labeled all of this. So right here we have our two variable quantities. What's the volume of a cylinder? Well, a cylinder is just a circle extended out. So it's the area of a circle, pi r squared, times the height of the cylinder. The radius of the cylinder is x. Well, so that tells us the area of the circle portion of the cylinder is pi x squared. Okay? That's the area of the circle. What's the height of the cylinder? Well, the height of the cylinder is this distance. Well, this distance is all of h without y. So the height of the cylinder is all of h without y. So the volume is pi x squared times h minus y. Well, that's great. H is a constant, pi is a constant, but x and y are both variables. So we're going to need to eliminate one of the variables. And to do that, we will make an observation we haven't yet made this semester. This height is actually, I labeled it over here so I wasn't in the way of the cylinder, but this height is actually this entire distance. And if you think of a line being drawn there, we can actually use that to find a relation between x and y. And I'm going to do that on this board, and then I'm going to erase it once we make the substitution into volume, because I'll probably need both of these boards to do the remaining computations. Maybe I should draw it a little differently, so that it looks like it came from this instead of just a huge triangle. So right here we have r, this whole thing is h, that's y, that's x. We have similar triangles. You could do what? Angle, angle, angle to prove they're similar, since the radii are both parallel. A cylinder is flat. Well, I mean flat to an extent. Which ratio will we use? Well, let's do what? This side over this side is the big side over the big side. So by similar triangles, we have y over x equals h over r. Keep the sides in order, but y over x equals this side over that side. And we can use this to find a relation between y and x. You could use other similarity ratios if you want. I'll just use this one. Our goal with this is going to be to eliminate a variable. I like eliminating y, so let's solve this for y. So multiply everything by x. So y equals h over rx. In this example, we will see that those rules with limits and derivatives, well, I guess more with derivatives than limits, since we're not really doing a limit here directly. The rules where we can pull a constant out of the derivative will be very useful for organizing a problem like this. So y equals h over rx. So let's substitute that here. Pi is a constant, x squared, h minus h over r x. Well, that's just wonderful. A messy looking equation, but it won't be too bad. I have 3 different examples in my notes I could have asked you. This one is the least bad looking of all of them. So we have this function. Let's distribute this out. Equals, and when we're doing this distribution, I'm going to pull all constants out front. So equals pi h x squared minus pi h over r x cubed. So distribute everything, pull all the constants out. If you ignore all the constants, we just have an x squared minus an x cubed. That's not bad. But we still have to do calculus. So we want to show, we want to maximize the volume of the cylinder, show how we can get the maximum volume of the cylinder, and then maximize the volume. So we need the first derivative of volume. Well, x squared derivative is 2x. So 2 pi hx. Derivative of x cubed, 3x squared. So negative 3 pi h over r times x squared. Okay, we need to set this equal to 0 and solve. So let's factor first. Let's factor. What can we factor out? Well, all of these things have a pi, all of these things have an h, and all of these things have an x. So let's factor out a pi hx. You pull a pi, h, and an x out of here, all you have left is a 2. You pull a pi, and h, and an x out of here, you have a 3. You have a negative sign, because we didn't pull a negative out. Pull, what, pi, h, and x, so the pi and the h are no longer there, the r is still there. One of those x's is gone. But we're left with 1. Well, that's great. Now we have to set this equal to 0 and solve. It equals 0 when this equals 0, or when 2 minus 3 over r times x equals 0. Divide by pi h, you get x equals 0. Or when, what, 2 equals 3 over r times x. Add 3 over r times x to both sides. Multiply by r, divide by 3. So x is 2r over 3. Well, we have two values here. One of them is not going to be in our domain. If x equals 0, what would that look like? Well, x is the radius of the cylinder. A cylinder whose radius is 0 does not exist in 3 dimensions. And that's what we have here. It would be like a very narrow cylinder from top to bottom of the cone. But you can see, if it went all the way to the top, then the base of the cylinder would no longer be a circle. It would be a point, and a point does not have area. So extending a point would not have volume. So x equals 0 does not matter. That other point will matter, and that other point will give us the largest possible volume of a cylinder. Let's show that it does. And let's use the second derivative. It's actually easier to use the first derivative, I would say. If you use the first derivative, largest possible, I'll do the work for the second derivative, but I'll just talk through the first derivative. If you use the first derivative, you want to show that the first derivative is positive on the left of that and negative on the right. Well, take x equals r over 3. If x equals r over 3, you have positive times 2 minus 1. Positive times negative is positive, so it would be increasing. On the other side, you could choose just r. R is larger than 2/3 r. If x equals r, again, you have a positive, but here you have 2 minus 3, which is negative, so you get that it's decreasing on the other side. I'll use the second derivative. The second derivative, let's use this form up here. 2 pi h minus 6 pi h over r times x. So again, a couple power rules. Well, this one's what, x would be what, 1x to the 0, so just 2 pi h. This one, you'd get that constant times 2x, so that 3 becomes a 6 when you multiply 3 by 2. And now, in the other examples we did, our second derivatives were all just constants, but here we have a variable in our second derivative. And what we need to do is show that the function is concave down at this point. In the other ones, we didn't have to substitute the point because substituting the point would not have done anything useful. It would have just left it alone. v prime prime is negative 4, v prime prime, if v prime prime is negative 4, then v prime prime at, which one had a 4? I can't remember anything anymore. The pizza one, I think, had 4. So v prime prime, I don't know. Here we have to do a substitution. V prime prime at 2r over 3 equals what? Well, 2 pi h minus 6 pi h over r times 2r over 3. So now we have some nice simplification. What kind of simplification do we have? Well, the 2 pi h we'll leave alone. You could try a factoring thing here. I'm not going to factor. We'll see that we don't need it. R divided by r cancels. 6 divided by 3 is 2. Well, let's do 6 times 2 is 12, divided by 3 is 4. So minus 4 pi h, which equals negative 2 pi h. The second derivative is negative. If the second derivative is negative, it tells you the function is concave down, which tells us, so x equals 2r over 3 gives that, a maximum. And let's put a box around this because we think we're done. It would be very unfortunate if this problem were on your final exam and you did all of that work and lost a point because you didn't answer the question. Find the largest possible volume of a cylinder. It doesn't say find the x value that gives the largest possible value. It doesn't say find the x value and find the y value that gives the largest possible volume. It says find the largest possible volume. So let's do that. All we have to do is take this equation down here and substitute our x value and simplify. So let's do that. So volume at 2r over 3 equals what? I'm going to use... I'm going to factor it a little more. I'm going to not use this form down here. I'm going to take this form and get rid of an h from the inside. So factor out an h, you're left with a 1 here, and you're left with 1 over r and an x and a negative. So the volume at 2 pi over 3, or at 2r over 3, is pi h times 2r over 3 squared times 1 minus 1 over r times 2r over 3. So let's just simplify this. So that's what, 4r squared over 9. So I'm going to put the 4 and the 9 out front and deal with all the letters over here. So we have 4/9 times pi times h times r squared, then times 1 minus, well, how nice, r and r cancel. And you're left with 1 minus 2/3, which is 1/3. And 1/3 times 4/9 is 4/27, and then the other constants are all constants. So find the largest possible volume. Again, we just needed to set up so that we get an equation, and here to find our relation between x and y that allowed us to eliminate a variable, we needed to do a similar triangle argument. Similar triangle arguments show up in a few different spots of calculus. It could show up in an optimization question. It could show up in a related rates question. More like in the middle of the semester, I was thinking, well, I want to do something with similar triangles, and I was looking at the examples I had, and I decided I would rather talk about similar triangles for an optimization type question than for a related rates type question during the lectures. So definitely get a good visual for a problem like this. It is useful. And once you get the observation, it's really important to keep your variables organized. This is the type of question that I like on lined paper, or as you see, an unlined whiteboard. I like them because it allows me to organize well.